All right, hi everybody, and welcome to this review video on Chapter 6 in the fundamentals of heat transfer. Right, this is the fundamentals of heat transfer by Bergman, Lavine, Incropera, and Dewitt. This is the seventh edition, and today I'm going to be talking somewhat briefly about Chapter 6. So basically, to me, Chapter 6 sets up a bunch of conceptual things that follow for chapter 7, chapter 8, and chapter 9. So I'm just going to focus on conceptual part for chapter 6 because I feel, at least for me, the real value of the actual calculations and stuff come in chapter 7, 8, and 9 when they're applied to specific cases of convection, external, internal, for both of those being forced, as well as free convection for chapter 9. Okay, so today I'll talk briefly about boundary layers, laminar versus turbulent, developed or fully developed, just the general problem of convection, as well as dimensionless numbers and correlations, which these are all pretty big themes for chapters 7, 8, and 9 when determining convection, right? So let's start off with boundary layers. So just a quick conceptual understanding of boundary layers. Okay, let's say you have this plate, right? And you have some wind blowing over this plate. Essentially, what happens is in um, fluids, you have the no slip condition. No slip condition. And what does that mean? That means that here you have a molecule, right, that experiences some friction and gets stuck on this plate, right? So all of these molecules that are right against the plate have zero velocity. Okay, so I would say all molecules touching plate have zero velocity. Okay, where we have some u infinity, or you could just say velocity. Up here, velocity equals u infinity, right? Okay, so what happens is the first bit of air hits this and gets stuck, right? But you get this, for a flat plate, you get some sort of shape that looks like this. What this is this is representing the speed of the air molecules, right? So let me kind of do this. Okay. Yeah, this is going to be less than u infinity, where this is about equal to 0.99 u infinity. Okay, so it makes sense if the plate is not moving that all of the molecules along the plate are also not moving. And as such, for viscous fluids, a boundary layer develops such that the viscous forces cause a velocity profile that might look like this, right? Where this is u infinity. And so you can see that the boundary layer grows with time. And actually the boundary layer grows assuming no separation um, and such. The boundary layer grows for infinity. The boundary layer never stops growing, although it does appear to become more asymptotic as as the spatial coordinates increase, right? So really the important, maybe I can summarize kind of the important thing, is the boundary layer. So the viscous forces and friction, the viscous forces of the fluid combined with the friction of the plate create this boundary layer where everything inside the red is moving slower than outside of the red, or well, this blue line which is separating red from the outside, right? So everything moving inside is moving slower because of the viscous forces and the friction experienced. Okay, so this is the velocity boundary layer, which is, as you know, that the velocity um, of a fluid is important in something like the Reynolds number. Okay, and so the velocity affects the thermal, right? So the more viscous a fluid is, and the slower this boundary layer develops, the less heat transfer will occur. Okay, so there's both a velocity boundary layer and likewise there's a thermal boundary layer where, so like for thermal boundary layer, replace U infinity with T infinity, right? So um, everything outside the blue line of T infinity is T infinity, but everything inside the red is at a different temperature, right? A temperature that's closer to the plate temperature, whether that's hotter or colder, right? Which the temperature of the fluid also affects the heat transfer rate. Now, when you look at all the correlations and stuff, a lot of the correlations, what they do is they integrate over the boundary layer. And this book doesn't really go into a lot of detail about how those equations are developed. But essentially, they look at a differential heat transfer, integrate over the boundary layer, as well as integrate spatially along X, along the plate. Okay. Um, I don't know, the boundary layer idea, for at least for the heat transfer, is not critical for you to understand. Um, if you're just looking to get numerical values from the correlations and such, right? But conceptually, it is really important to understand that because of the viscous forces, this in because of the viscous forces, the fluid is not flowing with an even velocity over the spatial coordinate x, if x is this way, of the plate. Okay, and that affects the thermal, so that affects the convection from the plate to the fluid, and that affects how the correlations were developed. Okay, so now laminar versus turbulent, right? So if you imagine this plate, all laminar is saying is that the molecules are, they're just go in a streamline. Right? So this is called the streamline. Okay, for turbulent, what you get is somewhat of a recirculating flow, right? Okay. Many times it starts out as laminar along a streamline, goes to turbulent. Okay. So turbulence is really hard to predict. Laminar is really easy to predict. Turbulent is so difficult to predict because you have these recirculating flows, right? So something, this molecule heats up, uh, not floats, but it it moves upward in space and cools down a little bit and comes down, right? And heats up and cools down, right? So you get these recirculating flows that are really hard to predict. Okay, so again, I'm not sure really what does this mean, right? Like how does this affect your calculations, right? For a plate, it's laminar when it's less than or equal to 5 times 10 to the 5th, right? For anything with a diameter, it's less than or equal to like 2300, I think, in this book. right? Otherwise, use turbulent. Okay, developed versus fully developed. Okay, so this again, this goes to viscous forces, thermal consideration. So um, let's say we have this pipe, right? Okay, so um, as we talked about, you have some fluid coming in right here, hits this, and then because of the viscous forces, the boundary layer starts to grow, right? And likewise on this side, the boundary layer starts to grow. Okay, until the boundary layers meet, this is called developing flow, whereas this one is called fully developed flow. So developing and fully developed flow is really important in internal flows. Right, so this isn't something that we'll look at in chapter 7, but we will look at in chapter 8. And that just affects what correlation you use, right? Because when you're integrating over the boundary layer, you can see here, the boundary layer is not changing. It'll never change. It'll always stay right here in the middle. Right, so integrating over the boundary layer here is much different than in the red, where the boundary layers have not met yet because it is changing, right? So that affects the correlation. So really like chapter 6 sets up a lot of how these correlations were developed, even though it doesn't walk you through the math, right? But this is showing you why these things, why developed versus fully developed is important because it changes how they do the integrations. So I guess, I mean, the problem of convection is just finding H, right? And as we see, most oftentimes, the convection coefficient H is a function of temperature, and temperature is a function of H, right? So temperature is a function of H, which is a function of temperature, right? And so this is somewhat of a problem with convection, right? But the whole problem of finding, the whole problem of convection is finding H. Okay, and then just dimensionless numbers and correlations, right? So Reynolds number is the biggest, right? So for example, the Reynolds number says if turbulent or laminar. So I would encourage you to look at table 6.2 because this gives good conceptual definitions of dimensionless numbers, right? Because, for example, the BO number, right? Ratio of the internal thermal resistance of a solid to the boundary layer thermal resistance, right? Friction factor, dimensionless pressure drop for internal flows. Mach number, ratio of velocity to speed of sound. Nusselt number, the ratio of convection to pure conduction heat transfer. Prandtl number, ratio of momentum and thermal diffusivities, right? So these are really good things to look up because they give you good conceptual definition of what a dimensionless parameter is. So I think chapter 6, I wouldn't focus too much on chapter 6 when studying for the exam because really what it does is it just sets up chapter 7, 8, and 9, right? And so you got boundary layers, velocity, and thermal, which affect if it's developing or fully developed, it affects the correlations that you're using, because the integrations to get those correlations were done differently, as well as it's the same case for laminar and turbulent. And then, yeah, just look at table 6.2. I think that really helps you understand why you're using a certain dimensionless number in any given case. So hope that helps. Again, this is just kind of a really quick review of chapter 6, because I feel a lot of focus should be given to chapter 7, 8, 9, where the actual calculations and applications of these principles are met. So, well, have a great day, guys. And again, good luck on your exam, and let me know if you have any suggestions on what I can do better, or ideas for future videos. So.